Alright, this week's topic is basically crystal deformation, which is the structure, the architect of geology. So a lot of these landforms we have seen, Anticlines, Synclines, we've talked about faults, we've talked about the San Andreas Fault. But today we're going to focus on the forces behind those, the forces that resulted in the formation of those. And that's what basically crustal deformation or structural geology is about. This basically involves physics and math. There's a whole subdiscipline of geology called geophysics. This is where you take physics and you apply it towards geology. So basically structural geology is the structural geologists study the architectural process responsible for deformation of the Earth's crust. So in other words, we look at the physical forces behind mountains that uplift, between valleys that downdrop, how faults react on the surface of the Earth, why they generate earthquakes. So this is all basically the essentials of physics. So as it turns out, when rocks are originally deposited, they're deposited flat and horizontal, like pages in a book, one sequential layer on top of another. Once faults occur, though, they start to move things around. So there's different types of forces at play. There can be tension. This is where the landmass is stretched, and I showed you a good video of when the North American continent overrode that Farallon plate. That Farallon plate went underneath the North American continent. Once that Farallon plate was consumed, the North American continent made contact with the East Pacific Rise. That East Pacific Rise is now underneath California. It's attempting to spread and it's stretching out the landscape. So when you stretch out the landscape, you create a series of cracks. Those cracks then have movement. Faults that move downwards. So this is actually a good test question. Faults that move down are what we call normal faults. Why normal? Because they follow the laws of gravity. When we compress the landscape, when we push things together, we ripple the landscape, we upfold it, we downfold it, we basically uplift the landscape. And this is a series of anticlines and synclines. The landscape becomes shortened, but it becomes taller, forming mountains. And so when a fault moves something upward, we call that a reverse fault. Opposite of a normal fault actually follows the laws of gravity. It drops down. A reverse fault defies gravity and moves upward. And then there's the shear stress. Basically, this is where plates slide past one another. So plates that are sliding past one another, this is what we call transform or shear. And this is basically, again, this is extensional tectonics, which we're going to stretch things out. But it's a little bit different force. This is where we have two plates sliding past one another. So the three major forces in geology are basically tension, we pull things apart, compression, push things together, and shear, where things slide past one another. So those are the three major forces in geology. So deformation is the general term basically used to describe what happens to rocks after they're deposited. Once they're deposited, they can be subject to compression, tension, or shear, and that's dramatically going to impact the rock and the landscape that it forms. So most crustal deformation occurs along plate boundaries, and this is very much true. When we look at the geology of the United States, we discovered that the mid part of the United States, Ohio, Kansas, Nebraska, they haven't had any continental margins. They haven't had any tectonic activity. That's why we don't find mountain ranges. The places where you do find mountain ranges are associated with, and somehow, with a plate boundary. Either plates converging, plates sliding past one another. This is what results in mountain building. So deformation involves force, the force of those great big plates moving. Those forces collide sometimes those forces move away from one another. And this is really important. So the mass of these continents are just humongous, a lot of weight there. They don't really move fast, so there's acceleration, not like an automobile, fast acceleration. These are plates that move by centimeters, millimeters per year. And over geologic time, that centimeter per millimeter per year adds up. So it took the North American continent and the African continent and basically Europe to separate, forming the Atlantic Ocean. That took 200 million years, and it occurred at a couple of centimeters per year. So as rocks are compressed, they can be shortened, and then they fold up folds, which we call anticlines. So definitely know what you definitely need to know what an anticline is. So anticlines are rock units that fold upwards. So anticlines, they fold upwards. Synclines are the opposite, they fold downwards. And this is all due to compression. So this is basically when rocks compress. Faults, where blocks of rocks like this one had moved up, would be a normal fault. So at one time, this block of rock was down here, it has moved up, and this is what we call a reverse fault. So we look at strata. Generally, we looked at the law of superposition, where the oldest rocks are on the bottom, the youngest rocks are on top, and that geological units are formed in large, continuous areas, and then they're subject to weathering, followed by erosion. A lot of the rocks are then taken away, redeposited somewhere else, and sometimes we see remnants of what was a continuous layer of rock. We see strata that is compressed and deformed into anticlines and synclines. We often see geological strata that's intruded by igneous rocks. Either can form a sill or a dike. A dike cuts across bedding. A sill cuts with the bedding. And then when we talk about geological time, we talk about unconformities. So there's three different types of unconformities. This one would be an angular unconformity because you have rocks that are not tilted above here, and below are these tilted rocks. So this suggests that at one time these rocks were flat and horizontal. They were then subject to tectonic activity where they were tilted. Erosion occurs, and then new rocks are deposited, superposed on top of those to form nice flat sequential layers. And this is what we definitely call a erosional angular unconformity. So deformation involves stress. The stress that's applied to rocks in a given area, and the three different types of deformation, the three types of forces that exist. Compression stress, we push things together, shortens a rock body, but it actually uplifts it. This is the ones that form mountains. So compression, probably the most important. It creates anticline folds and syncline folds. It creates mountain ranges. It also creates normal or reverse faults and thrust faults. So the stresses of compression, what compression actually does when we push rocks together, we basically result in reverse faults, thrust faults, anticline folds, and syncline folds, and generally uplifting of mountains in general. Tension is when we pull things apart. So the major structure that results from tension is primarily normal faults. These are blocks of rocks that move down. Death Valley, that huge valley, was formed due to tension. It was dropped down along normal faults. So that valley, that basin, is 283 feet below sea level. It was a result of tension force. And then shear is kind of a tricky one. This is basically when things slide past one another. The San Andreas Fault is currently doing that, where everybody that lives on the west side of the San Andreas Fault, you live on a plate that's moving to the north. Everybody that lives on the east side of the San Andreas Fault, say Barstow, they're moving to the west. So this is where two plates slide past one another, and this is how shear stress is performed. So compression. We shorten the landscape, we uplift it, forming mountain ranges, and we form these folds, anticlines, up folds, synclines, down folds, another anticline, a syncline, an anticline, and so forth. We just get this continuous folding structure, and this is due to compression. If you look at the United States, we talked about this when we talked about the geology of the United States, and then we spent an entire class last time dedicated just to California. We see all these different colors here are different types of rocks. And so California, first it was basically a very laid back setting. It was basically what we call the Atlantic type of continental boundary, where it was the trailing end of a continent, no tectonic activity. And then that kind of abruptly ended about 200 million years ago, and California since then has seen compression and extension. So basically California has been subject to all of the forces. And that's kind of rare, because usually if you look at a landscape like the Great Plains or the coastal areas of the United States, they've been basically subject to maybe one force, tension, where California has been exposed to all three major geophysical forces, which has really resulted in a dynamic landscape that we have. So California, the entire Rocky Mountains were subject to compression when continent-to-continent collision occurred, when ocean-to-continent collision occurred, and subduction and magma moving up. This created the fold belt of the Rocky Mountains. When South America collides with North America, it creates this Ouachita uplift, basically creating the Ozark Mountains. When the African continent collided with North America, forming Pangea, it created a fold belt called the Appalachian Fold Belt. Here in the mid part of the United States, nothing tectonically going on, no really applied force, a little bit of compression, and I'll get into that because we're going to talk about basins and domes and how important they are to natural gas. Very highly volatile politically right now because of the proposed ban and political stand against fracking, and we'll talk about that later. So compressional structures, thrust faults, anticline faults, syncline faults. Faulted rock in general is going to be compression. So whenever you have a compressed force, when you squeeze something together, push it together, you're going to uplift those rocks. So that's compression. Probably the most dynamic force in nature, the one responsible for mountain ranges, so it makes our landscape not so boring with the formation of mountains. So here's a good example of compression. These rocks here violate Stirnow's law of superposition. So in the law of superposition, we told you that the oldest rocks are at the bottom and the younger rocks are on top. Here, the opposite is true. These rocks are Jurassic in age of the dinosaur basically, from Jurassic Park, 170 million year old rocks. Overlying them though are older rocks. It's supposed to be the younger rocks up here, but these are the older rocks. And that's due to compression. When a piece of California collided, it literally, when actually a piece of the Rhodian continent collided with California, it took a piece of California and shoved it all the way to Nevada. So these rocks are actually in Nevada, just west of Las Vegas. And here we find older rocks, Devonian age rocks, 400 million year old rocks superimposed on top of Jurassic age rocks, which are considerably younger. So this kind of violates Stirnow's law of superposition with the old rocks on the bottom and the young rocks are on top. And this is what compression does. It violates laws. It creates mountain ranges. So extension, this is when we start to pull apart continents. We saw this in the basin and range. The San Andreas Fault today is basically stretching the entire western United States. So it's like taking a piece of paper here. This part is going this way, and this part wants to move north, so it's just stretching everything. And eventually you stretch it, it's going to tear it and destroy it. And this basically what is occurring in the western United States. So valleys like the Phoenix Valley, where Phoenix, Arizona lies, is a great big basin. Las Vegas is in a basin. Barstow's in a basin. Victorville. All the major cities are in basins, and these basins have been created by extension. As we pull the landscape apart, the mountains down drop, and we form these great big basins. So first, when you have this tensional force, you basically pull things apart, and then that creates a lot of cracks. These are stress cracks reliefs. More pulling, these cracks start to move. A crack that moves we have to classify now as a fault. So the difference between a crack and a fault is simply movement or no movement. So if it's a crack, there's no movement. If it's a crack with movement, it now becomes a fault. So primarily, here the valleys are down dropping along normal faults. So normal faults is when a block of rock moves down. And we saw this in the western United States, so basically the entire state of Nevada, a little bit more in Utah than this is the diagram showing. Southeastern California, southern Arizona, southern New Mexico, and extreme western Texas. This is where this area is being stretched. The entire, basically, western United States is being stretched right now because of the San Andreas Fault. Because Baja and everything that's on the west side of the San Andreas Fault is moving north against the North American continent, which is moving west. So everything's being stretched. So it's like this, if you have the continent here, it goes right across the fault. This part's going this way, but this part's going like this, and it starts to stretch and elongate that entire landscape. I'm destroying a lot of this green paper, but that's okay. So Death Valley, huge basin below sea level, formed basic due to the downdropping of the valley along normal faults. So rocks that are not deformed, this is what Nicholas Sternal recognized. He says that here, this is the youngest rock, and as we go down, these rocks become progressively older. And so these are strata that's not deformed. There has been no really applied force in these rocks whatsoever. And this is why they are pretty much in the original position in which they were formed. They have not been subject to compression or extension or tension in any way. And these rocks, though, have. At one time, these rocks were flat. They were horizontal. Much like the rocks in the previous picture, they've been compressed, and as they compress, they start to fold these structures. So here, great big syncline fold, and here's an anticline fold. Back in the good old days, when we actually had face-to-face learning, we would do field trips, and this is one of the places we would stop on our historical geology field trip at the ghost town of Calico. So if you ever go to Calico Ghost Town, if you park in the upper parking lot, walk to the edge of the parking lot, and this is the view you have. There's actually a truck with a camper shell on it to give you the scale. So these rocks, compression, they upfold, and then they can be subject to weathering and then erosion, and you form a modern landscape. And sometimes you would not know you were walking across one of these upfolds. So what's neat about these upfolded rocks like this is these are really important for oil. So in Southern California, we find oil in anticline folds. So here, if you're looking for an anticline, how do you know this is an anticline? By walking across the surface. And essentially you don't unless you're able to pay attention to which way the rocks are dipping. So as you're walking along here, these rocks are dipping that way. Then you walk further, these rocks don't have a dip. And then you walk over here and you say, well, these rocks are now dipping this way. So you stand there and says, okay, those rocks are dipping this way. That means they're going up like this. These rocks are dipping up like this. So, anticline. And this is how geologists find oil. Some of these anticlines are very noticeable. This is a huge anticline outside of St. George, Utah. This is what it looked like before development, and this is post-development. So they built a dam across here and created a man-made lake. These are some agricultural fields out here. And so here, these rocks, these are upfolded rocks, and this is a great big anticline. So this is an anticline that doesn't go vertical, this goes horizontal across the landscape. So these fault structures can be vertical or they can be horizontal across the landscape. So the second type is tension. This is where we pull things apart. This is the current situation in Western North America, certainly in California, Death Valley, and this has resulted in the development of the basin and range. And so we talked about that in previous lectures when we talked about the geology of the United States, and we paid particular attention to places like Nevada and Utah that are being extended. And this is along normal faults. So the San Andreas Fault, this is what's really neat about the San Andreas Fault. Everybody thinks it's a California geological phenomenon. They're wrong. What is occurring in California is impacting the Rocky Mountains, is impacting Nevada, Idaho, Oregon, Utah. So as the San Andreas Fault stretches North America, it's having a ripple effect that's being felt all the way into the Rocky Mountains. It's amazing how dynamic the San Andreas Fault is, and what we've learned in the past 115 years since the 1906 San Francisco quake. It's just amazing what's come out in studies, and the parameters of the San Andreas Fault is really interesting. So here we have our current landscape where we have our San Andreas Fault, which is really a system of faults, not just one linear line. It's taken the Baja Peninsula and ripped it away from Mexico. And so everything that's on the west side of that line is moving to the north. Everything that's on the east side of the line is moving to the west. And so it's kind of taking the landscape along and it's stretching it. So basically, eastern California, all of Nevada, all of southern Arizona, Utah are being stretched by this. And here's a great big valley right here, and this is actually Death Valley. So these huge valleys, these basins are being downdropped because of tension. So Death Valley, this huge downdrop valley, is just amazing. All right, so deformation. How do we deform rocks? Well, we put strain on them. So strain is going to change the shape and the size of the rock body caused by the stress. And how rocks deform is really dependent upon what the rocks are made of. Sedimentary rocks, rocks like shale and sandstone, have a greater chance of upfolding into anticlines and synclines. Granitic rocks, because they're very hard rocks, they're very well compacted, they were solidified because of hot magma, they cooled and solidified, those rocks have less of a tendency to fold. And as a result, they'll break, they will crack to the point where they won't fold. Sedimentary rocks will fold, and most igneous rocks will not. So they all act slightly different. So the general characteristic of a rock is really important. How elastic a rock is. So this paper here is pretty elastic. I can fold it. I can make it into nice anticlines. I can make it into synclines. And if I'm careful enough, I can make both anticlines and synclines on the same page. Look at that, 2 anticlines and 1 syncline. So this is very elastic. Glass, is it elastic? Can I take a piece of glass and say this was, pretend that this is glass? Can I push it and strain it? Well, it would crack first or break. Unless I heated that glass. If you heat that glass, then you can bend it. So sometimes rocks that are buried under depth and subject to heat are more vulnerable to folding. And so the elastic limit, once that elastic limit is exceeded though, this is when the rock is going to form a fracture, a crack basically, and then you're going to get moving along that crack, and this is basically going to result in the formation of a fault. So this is a good example here where these rocks are pretty elastic, they folded pretty nicely into the nice upfolded anticline, and then the syncline here. But look right here. So right here, you can see the straight line where this ridge and this ridge are kind of offset here. That is a fault. So what's occurred in these rocks is that the elastic ability of this rock has been exceeded. And so when you exceed the elastic limit, then you're going to basically result in brittle fracture, cracking, breaking. And once that crack appears, that crack is now going to release some of this stress, and it's going to move, and at that point, we would call this a fault. So the type of fault that's here is that this ledge here used to be down with this ledge here, and they've been offset, and so therefore that was a good example of a reverse fault. So I have some better pictures. So now elastic break. Glass has a little elastic quality to it. Paper does, it'll fold. Rocks act in a similar way, so it depends on the type of rock, whether it will fold or not. So here's a good example of a fault. So if I was to take you on a field trip here, and we actually stop at this place on a field trip, and we all got out of the car and says, okay, this is your quiz. What type of fault do you see here? Is this a normal fault, or is this a reverse fault? So you look at that and you might say, So if it's a normal fault, this yellow layer and this yellow layer up here, you would say were together at one time. And so if it's a normal fault, you would say that this block of rock moved down. That would be a normal fault. But what if this yellow layer here was down here, and this whole block of rock moved upward? Then it would be a reverse fault. So how do you tell if this went up or that went down? Or maybe they both moved. That's kind of rare that they both move. It's generally one or the other. And in this particular case, you have to really look at the dynamics of the crack here and look for elongated pebbles and the orientation of those things, and it would tell you that this is actually a normal fault. That this block of rock here actually came down. So this is a normal fault. This is actually in a road cut called the Charles Brown Highway, not named after Charlie Brown, the Peanuts character, but actually named after a state senator, I guess, back in a long time ago. All right, so deformation. So rocks are going to either fold or they're going to fracture. That depends on temperature. So if you increase the temperature, there's a higher probability that rocks are going to fold. Confining pressure means that they're buried. Rocks that are buried, where that stress cannot escape, that force cannot escape, they're basically going to fold. The rock type, granitic rocks, very resistant to folding. Sedimentary rocks will fold. And then time, how much time you have, millions of years, and this allows rocks to fold. Okay, so what we do is we're going to take all these geological structures and we're going to map them. And these are some pretty neat things that we can do with maps. We can actually help determine hazardous locations. We can actually look at areas that are suitable for building. And so there's a lot of useful information that comes out of geological maps. I like the old paper maps because they're really useful. I mean, I have some really old maps, and there's things on these old maps that were made like, God, in the 1950s that don't show up on GPS. I was actually looking for a mine called the Green Monster Mine that has a mineral called malachite, and it's also slightly radioactive. And I want to test out my Geiger counter, so I couldn't find it on the new maps, on the new GPS, and I found this old 1956 map of the Mesquite Valley Quadrangle, and I found it. You know, you look at the latitude and longitude and went right to it. So old paper maps, there's something to be said for those. So what we do is we can use satellite images, and satellite images are really cool. A couple things came out of this. We can see our San Andreas Fault right here. And there's another fault called the Garlock Fault. This is actually during October, during the height of fire season. So all the red dots represent fire. So this shows the Santa Ana condition with the winds blowing offshore, taking all the smoke out there. Black and white photographs are very powerful because you have black and you have white, and in between is gray. And so there's a lot of digital information. So black and white photographs are more powerful sometimes than color photographs. And then this is a project I did when I was a graduate student. We had to actually I took an advanced GPS class, and one of the things that we had to play around with was different bandwidths. So I forget what bandwidths I used on this particular project here. I used the transfers from K to UTM, but anyway, what I was focusing on here was two things. Volcanic rocks and their distribution, and also these are fields of agriculture, so these are agricultural fields. And as it turns out, infrared takes everything that's green and turns it red. But it also can give you different shades of pink to red to basically to maroon. And this can tell you what type of crop grows. The DEA uses this. They fly over the Santa Ana Mountains and they find this weird color out there, and they realize that people out there growing marijuana. That's how they bust those people way out in the middle of nowhere. Those rangers aren't going out there hiking through the trees. They're flying over the plane and they're shooting with some GPS, some film, and they're basically digitizing it and showing this weird color of green out there, which is actually red. Low altitude aerial photographs are pretty cool. This is out in a place called the Wonderful Valley. I don't advise that you live there. These people live there, and they built their house, and this is a geological fault that goes right through the home. We stop at this place in one of our field trips when I teach historical geology called the Palmdale Bulge. And you can see the San Andreas Fault. You can basically stand out and look down the valley, and you can see the San Andreas Fault. And there are houses that are built right on it. One of these days I'm going to take my field trip class and we're going to stop at one of these houses and knock on the door. Hey, do you realize your house is on the San Andreas Fault? Well, that'll be interesting. So this is actually a fault that occurred. When I went down to investigate this with some friends. This happened in 2010 near Mexicali. And so this is basically two plates that moved. This plate basically went in this direction and this one went in that direction. You can see a little offset there. This is one of the highways, and it's kind of hard to see from this picture, but this part of the highway moved over this direction and this part moved in that direction relative to one another, created this great big area that collapsed in. And then what's nice about geological maps is we can actually put down different geological faults. So this basically is a map showing Southern California with the Palo Verde Peninsula here, Long Beach, Huntington Beach would be here, and all these different red lines are different faults. And the colors are the probability of earthquakes. So if you're in a red area, you have a higher probability versus green, which has less of a probability of a major earthquake. So this is very interesting information. So our end product is going to be some type of geological map. They can be used for land use, they can be used for hazardous regions, they can actually map out resources, where there's oil, where there's mining potential. And this is one of my favorite maps. So this actually shows a map with a bunch of red dots. And each one of these red dots represents an earthquake that occurred between 1940 and just a couple years ago. So each red dot is an earthquake. And what's neat about this is applied calculus. So people say, well, what good is calculus? Oh my God, I hate that class. Well, here's a good example. So here, notice that all the red dots form a nice little linear line right here. Can you see this? Nice linear line here. There's another one here. There's another one here. So you can see where these dots actually form a nice linear pattern. Those linear patterns are faults. So here's the San Andreas Fault. Here is the San Jacinto Fault. There's the Elsinore Fault. So you can basically use data like this, just the distribution of earthquakes, and you can actually create a regression analysis. I remember when I was an undergraduate, I was living in the fraternity house, and all the guys would come to me about their math problems and their science problems, because I was majoring in, obviously, science. And this guy comes to me and says, dude, man, I have to do this regression analysis, and I don't even know what it is. That's why you just take a bunch of dots and data, and you draw a line through it. And so we actually can use this to actually trace out geological faults, like the San Andreas Fault. And so once we get that information, we can put on a map. So this map is really useful because it tells you the earthquake potential of faults. So in this case, the black line here, the San Andreas Fault, has a potential of generating an 8.0 or greater magnitude. The yellow or the red lines, such as the San Jacinto Fault, the Elsinore Fault, and the Newport Inglewood Fault that travels right along the coast, that has a potential between a 7.5 and an 8-point earthquake. The mustard color between a 6.7 and a 7.5, and the yellow 6.7 or less. So this basically is useful information to determine the earthquake potential. So you can see California, we're kind of in trouble. Red line, red line, red line, and the big black one here. So even in Orange County here, we lie between the Elsinore and the Newport Inglewood faults. So we have a very high potential for earthquakes in Orange County because of the proximity of those faults. So we map these geological structures. We look at the trend of mountain ranges, which way they're trending. We look at the attitude of the rocks, the dip. I talked about that on a field trip that we went on for the 110 class. And so basically the strike is the compass direction of the mountain range. So that's the general trend of the mountains. So say you have a mountain range that's uplifting. So here's my mountain range, okay? And what I can do is I can take a compass and I can say this mountain range has a northwest, southeastern orientation, or I can say it has a north-south orientation, or I can say it has a southwest, northeast orientation, and that's basically the general trend, the strike of the mountains. And then the dip is the attitude of the beds if they're dipping at 30 degrees. So originally, remember that all rocks are deposited horizontal. These have been subject to some tectonic activity here. So you got this tectonic activity here that has tilted these rocks. So in this case, these rocks are dipping, and if you follow the compass directions, these rocks would be dipping towards the east. Since north is at the top, south would be the bottom, west, east, these rocks would be dipping to the east at 30 degrees. And that's kind of important because if you're looking for structures that are going to trap hydrocarbons or oil, natural gas, you really have to pay attention to the direction of inclination. The Grand Canyon, and we've talked about this quite a bit when I talked about the geology of the United States, the rocks there aren't tilting. They're flat, they're horizontal, which is kind of neat because most of the rocks surrounding the Grand Canyon, such as the Rocky Mountains, Nevada rocks, Arizona rocks, are tilted. These rocks are flat, they're horizontal, sequential layers. You find the oldest rocks at the bottom, you find the youngest rocks at the top. So what's neat about the Grand Canyon is that there are rocks that are 540 million years old that are sedimentary. Below that are even older rocks that are igneous. But we're going to be biased here. I'm going to talk only about sedimentary rocks because they're the coolest rocks. They have fossils, by the way. And so as we go up, the rocks become younger. So you start at a 540 million year old rocks, and as we go up through this sequence, by the time you got to the very top, to the Permian, these rocks are basically 200 million years old. These are the Permian Kaibab limestones. So this rock formation, the Grand Canyon, follows Sternal's law of superposition. There are some unconformities in there. And then so we map these structures. We look at the dip, the inclination. In the case of the Grand Canyon, there is no dip. So these basically are flat rocks. And that's what we see in the Grand Canyon, no dip. But this mountain range violates that because it's been subject to tectonics. So at one time these rocks were like this, but now they're dipping. So you can see there's almost like a 45-degree angle. So the strata of this unit has been dipping. So we have to pay attention to this. And this is what's interesting. I took this shot of a helicopter when I went to the Grand Canyon one time. Excuse me. Wow. So these rocks here are flat, they're horizontal. Then these rocks are tilting. So this kind of suggests that between these rocks and these rocks, there might be a fold structure. Maybe a syncline. Yeah. I'm not going to go look for oil over there because there's a syncline. I'm not going to find oil there. So forget that. Oil exploration, people go home. Now, this is what's underneath. I can't see this. But here's an anticline, and here's a syncline. So my job as a petroleum geologist is I have to go find oil. That's my job. I have to put an X on this map and tell the drilling guide to drill here at this X. So how am I going to find where the anticline is if I walk along the surface here? So pretend you can't see this, okay? I'm going to cover this up. You can't see it. I need to get a piece of paper and cover it up. So as I'm walking along here, I take a reading on this and I say, well, the sandstone formation is dipping to the west at 30 degrees. Walk along here, and I find this other sandstone formation. That formation is dipping at 85 degrees to the east. That's the opposite of what I just saw over here. So that tells me that since these rocks are dipping that way, these rocks are dipping that way, superimposed on top, what do I have? I have a great big anticline right here. So if I want to tell somebody, and I want to keep my job as an oil petrologist, I'm going to say, right there. That marks a spot. We're going to hit pay dirt. We're going to get a lot of oil. If I was over here and I decided to drill the oil here, and I said, well, these rocks are dipping this way, and these rocks are dipping this way, so this is dipping this way. This is dipping this way. This is going to form my syncline. So even though we can't see underneath, so this is like if you have a marble cake and it's all covered with icing, you can't see the marble cake, the layers of the marble cake. So here you cut it into a cake and you take it out. And now we can stick a fork in it and eat it. It'll be good, right? All right, so folds. So during crustal formation, rocks often break, into a series of wave-like folds. And what I want you to know for the test, I definitely want you to know, anticlines are upfolds, synclines are downfolds. So really, please, note those two important characteristics of folds. And then, the book gets into plunging anticlines and plunging synclines. These are anticlines that kind of have both a vertical and a horizontal component to them. And I'm not going to worry about that so much. We're just going to look at these types of anticlines and synclines. So here is a great big syncline. So in a test situation, I'm going to tell you the rocks are downfolded. You're going to tell me it's a syncline. If they're upfolded, you're going to tell me it's an anticline. And that's basically what I want you to understand. So folds, anticlines are upfolds, synclines are downfolds. So it's kind of really simple. The way that I remember this when I was a student, syncline going down, they're the sinners, they're going down, okay? And that's how I remembered it. So depending on the orientation of the anticlines, sometimes they're like they can be symmetrical or asymmetrical. I'm not worried about that. If we were in a structural geology class, the book does go into this, is why I kind of mentioned it. So here, this is an anticline basically that is slightly plunging into the ground. So this side of it looks like this. So here is an anticline fold. Here's an anticline fold that is actually kind of plunging, so you get these nice little ridges. These are really common in Harrisburg, Pennsylvania. Pennsylvania, which is mostly made out of slate and metamorphic rock, has some beautiful anticline and synclines, and the Susquehanna River actually flows around some of these, which is really neat. And so these plunge into the ground, so they kind of go at an angle like this, so they're not perfectly vertical, they're not perfectly horizontal, they are kind of a combination of both, but I'm not too much worried about that. So how do anticlines and synclines fold occurs in California? So California has a series of anticlines and synclines. Where we have anticlines, we also have oil. So Huntington Beach, right around Golden West and Garfield, that's a hill right there. And so that's a huge anticline. So if you leave our campus and drive on Huntington Beach, or drive on Golden West, and you go towards Warner, past Warner, you go past Slater, and then right after Slater, there's a hill. You kind of go up right around the library, and then it goes down again. It goes back up around Goldfield, or not Goldfield, but Garfield, the name of the cat, Garfield. And so how do these anticlines and synclines folds occur in California? They occur primarily because of the fact that the San Andreas Fault is creating differential movement. So the rocks on the east side of the San Andreas Fault are moving to the north, but not really. They're moving really to the west. The rocks on the west side of the San Andreas Fault are moving to the north. So they're basically being dragged along. So as these rocks get pulled and contorted, they fold into anticlines and synclines. And it's the anticline folds, the upfolds, that have oil. So this is actually a picture of an area called the Palmdale Bulge. This is right on the San Andreas Fault. And the reason that these rocks act this way is because you have a lot of drag. Rocks on one side of the San Andreas Fault are moving faster than rocks on the other side. So since everybody's not moving along uniformly, there's differential movement that results in these downfolds and upfolds into anticlines and synclines. So this is where we find oil. We find oil along these anticline folds, so this is what geologists look for. They look for anticlines. This is an interesting map here, and I really like this map. So I actually did some changes on this map. So all of these green things here are oil fields, okay? So out here we have Kramer, Yorba Linda, Brea, Whittier, Montebello, Los Angeles. And you can actually draw a straight line connecting these, okay? I did that here. So in coastal California, we have Newport Beach, which is basically the same oil field as Huntington Beach, even though they say it's different, it's not. So here we have Newport, Huntington Beach oil field. We have an oil field in Seal Beach. We have one in Long Beach. We have one in Dominguez, Rockrantz, all the way up to Chevron Hills, and all the way to Hollywood. So you can draw a nice straight line connecting these. And this nice straight line happens to be the Newport-Inglewood Fault. So again, in this area here, the rocks on the east side of the San Andreas, of the Newport-Inglewood Fault, are moving slower than the rocks on the west side of the Newport-Inglewood Fault. Again, it's creating drag, it's causing rocks to upfold, so huge anticline here, there's a syncline here, anticline, syncline, anticline, syncline, anticline, syncline, very small one, anticline, syncline, anticline. So this is why we find oil scattered across California. It's not continuous because the oil beds are found in upfolded rocks and anticlines. So the Newport-Inglewood Fault runs right along the coast of California. It becomes offshore right where the pier is. So the pier was built there because that was a point break. This is where the shore kind of comes to a nice little point, and they decided that was a great place to build a pier. They didn't realize that that was also a place where the Newport-Inglewood Fault goes from landward along the coast and it goes offshore. And offshore we have a lot of oil derricks, so you can see the oil derricks out here. And these derricks are drilling into anticlines. Now, it's hard to imagine, like, you say, well, wait a minute, this is down. And you're right, this is down. There's an anticline out here that formed, and then this area was downdropped. So it's an anticline, was first pushed up because of compression, formed an anticline, and now that anticline has been downdropped into a basin. So basically what exists between the coast of Huntington Beach and Santa Catalina Island is a great big basin, but it's also a huge anticline. And that's where we find oil. So as you go north along the Pacific Coast Highway, so as you go towards Warner, you don't see any more oil platforms out there, and that's because there is no oil out there until you get over to Seal Beach. So oil found in these upfolded rocks, anticlines. So when they discovered oil on Huntington Beach, it was literally coming out of the ground in natural oil seeps. And those natural oil seeps is where the pressure of the oil is escaping through the sedimentary layers. So we are looking to drill at the top of the anticlines. That's where we're going to find the oil. And that's where you see these oil derricks right there. There's still a lot of oil out there, a lot of drilling going on. And basically these rigs are drilling into anticline faults. Alright, other types of faults. There's monoclines. These are basically, a monocline is a fault that has been buried by sedimentary rocks. And then domes and basins. Now this is really important right now because the United States has more natural gas reserves than Saudi Arabia. We have more natural gas than Saudi Arabia. They used to have more than we, by far. And today we're one of the largest holders of known natural gas reserves. And this is technology that has developed over the past 10 to 15 years, known as fracking. As it turns out, in the mid part of the United States, there are very slight downfolds and very slight upfolds. How slight? The entire state of Illinois is a great big basin, but it's a very subtle basin. You'd have a hard time recognizing this basin by going across the state of Illinois, but it's a great big basin. The entire state of Missouri and northern Arkansas is a great big dome, an uplifted area. So here's a monocline. Basically, it's an old fault that got buried underneath sedimentary material. And these faults are thought to be no longer active, but in some cases they have surprised people. And so basins are large-scale folds. The entire state of Illinois is a huge basin. And what's nice about these basins is over time they have accumulated hydrocarbons in the sedimentary rocks. And these hydrocarbons have produced, through the natural biological process of decay, and they form natural gas. The natural gas, though, however, is pretty dispersed. It's spread out. And so we have to use a process called fracking. And what fracking does is you put a well over here, you have another one over here, and you push, either with sound waves, salt water, chemicals, you push that natural gas over to your extraction well, and this whole process is called fracking. So if you look at the entire state of Michigan, so Michigan basically is a great big gigantic basin, so is Illinois, and we can tell by just look at the age of the rocks. So as it turns out, basins have younger rocks in the center and older rocks out in the edges. So as you go along this line here, you go from these purple rocks, which are Devonian in age. These rocks are about 350 million years old. You go to the Pennsylvania rocks, where the rocks are 300 million years old. So you see this age difference. This is how we know this is a great big basin. And so the entire, basically, state of Missouri and northern Arkansas is a great big dome. So domes or basins are really important because this is where we find natural gas. So as it turns out, most of the natural gas occurs in the bottom of these basins. And so we see these in states like Pennsylvania, Illinois, Indiana, Wisconsin. North and South Dakota really is prominent for these features. And this is why those states are really important for natural gas. And the process in which they remove that natural gas is fracking. So these fault structures are good geological structures for the trapping of natural gas, basins or domes. You do find some natural gas in domes, so it's not exclusively to basins, but certainly we find the greater concentrations of natural gas in basins. I mean, I have to put on the red tie here and pretend like I'm from the oil company for a minute. Natural gas, cleaner when burned due to less carbon, less sulfate pollution. It's good for you, it's good efficient energy. We need more natural gas. So a lot of ways the United States started converting from gasoline cars to natural gas. So all the OTOC buses, they run off of natural gas, and the natural gas comes from, some cases, landfills, dumps, old dumps that emit methane gas. A lot of fleet vehicles, a lot of companies have large fleets of vehicles, we use natural gas. And I think our natural gas conversion got kind of slowed down because oil has been relatively low. Certainly during the Trump administration, oil became pretty reasonable. Prior to that, it was pretty high, and gas was going to $4 a gallon. And so this is an interesting map here, and this just shows 2 years, which were kind of critical years for fracking. 2006 and 2007, a lot of technology emerged in this time between the years of 2006 and 2007. And so as a result, this new technology, when it was employed to some of these existing areas where natural gas was already known, they were able to basically increase the potential yield for natural gas recovery. So if you look at southwest Wyoming, they went from 34 units to 53. Woodruff Basin in Oklahoma from 12 to 17. Barnett, Texas went from 62 to 97. Fayetteville, Arkansas, and part of it goes into Oklahoma, 26 to 42. Haynesville, Alabama, look at this one, 34 to 251. Big potential for natural gas fracking. And funny thing is that if you start looking at, we'll look at this in a minute here, the Marcellus Basin, actually upper state New York, 34 to 62, and Atrium up in upper Michigan from 13 to 20. So this shows that natural gas, known reserves, has increased due to technology. So this is basically due to technology with the fracking. So the funny thing is that look at where the basins are, and those are the states that generally vote red, such as Texas, Oklahoma, Arkansas voted red, Alabama. And then Pennsylvania, which some people say really did go red, but maybe it didn't go red, I don't know. I guess there's a lot of voter fraud being discovered out there, which is sad. Alright, so this is some of those basins. So even out here in California, we have a huge basin. The San Joaquin Valley has a lot of natural gas in it. And then New Mexico is really utilizing a lot of natural gas out of the San Juan Basin. And there's a lot of natural gas. So these are the basins that really contain, so look at all of the Appalachian Mountains. High potential for natural gas. And so the United States has a really high potential of natural gas. The bad thing about fracking is that it's become a political football, and it shouldn't be. Some places it's okay to frack with no environmental problems. In other places it is an environmental problem. So what should be the determinant of where we frack and where we don't frack? Purely based on science. It's not the kind of thing that politicians should be deciding without a background in science, without at least good, solid scientific work to back that up. So it shouldn't be the political football that it is at all. Alright, so let's look at faults. Faults are fractures in rocks in which there's been displacement, movement basically. So sediments along faults cause earthquakes. So we talked about earthquakes earlier in the semester, and we went through an entire history of earthquakes. Faults are classified by their relative movement, which could be horizontal, vertical, or oblique. And the book has this terminology, and I think it can be kind of confusing. So this is what I want you to know. So look at this fault here. Dip-slip faults. Movement is mainly parallel to the dip of the surface. May produce long-lying cliffs called fault scarps. Parts of a dip-slip fault include hanging wall, footwall. This is what I want you to know. A block of rock that moves down is a normal fault. A block of rock that moves up is a reverse fault. Older rocks pushed on top of younger rocks are always going to be thrust faults. And faults where plates slide past one another are transform faults. Those are the faults I want you to know, plain and simple. So the book, I think, kind of takes the simple terminology of faults and it complicates it, unnecessarily complicates it. And so miners would look at faults because a lot of mining ore veins tend to follow faults. So in this particular photograph, the miner is standing on the footwall with his foot, and what's above his head is the hanging wall. But miners actually call it the head wall because that's what you bump your head into. And then there's all these definitions. Normal fault, hanging wall block moves down relative to the footwall block. I want you to know, a normal fault, a block of rock that moves down. And that's exactly what I'm going to put on the quiz. I'm going to say I have a block of rock to move down, this is, and you'll have your choices. Block of rock that moves up, reverse fault. Okay, we're going to make this simple. So again, go back to our picture right here. This is actually a normal fault. This block of rock actually moved down. That makes it a normal fault. Here's a road cut, pretty interesting. So you can see the offset here between this and this. In this particular case, this block of rock here moved up. Therefore, it is a reverse fault. So what I would do when I would draw faults on tests is I would draw a picture and I would put an arrow to the one block moving up. So I put an arrow on that, relative to the block of rock moving down. And so here's a neat road cut. I was on I-40 one time and I just had to go back and get this picture from a distance. So you can see this is a road cut here, and there's a fault here, there's another one there. And so in this case, these are actually reverse faults. These rocks have been pushed upwards, creating these reverse faults. So they talk about the hanging wall and the football, and see, diagrams like this are confusing. They say, yeah, well, this wall moved up relative to this wall moving down. And so when I put these arrows in here, I superimpose these arrows, this means it's compressing, which means this rock moved up and upward to this mountain. This will be a reverse fault. And then there's the reverse faults. These are also known as thrust faults. The difference between a reverse fault and a thrust fault is the angle. So thrust faults are low angle. They're like 45-degree angles. And one of the things that you'll always find in a thrust fault is you will always find that older rocks are on top of younger rocks. Always. That is generally the case. So here's a good example of a thrust fault. Low angle, about 45-degree angle here. And basically these rocks have been pushed on top of these younger rocks. And so thrust faults always have young rocks that are overlying by older rocks. So the older rocks are on the top. They're supposed to be on the bottom, but they're not. This violates Stirno's law of superposition. And then there's strike-slip fault. So the San Andreas fault is a strike-slip fault. But technically the San Andreas fault is also what we call a transform fault. That means a fault that's along a plate boundary. But faults that move side by side are always known as strike-slip faults. The San Andreas fault is a strike-slip, but we also give it a little bit of higher designation. We call it a transform fault because two plates have slid past one another. So this is a good example of the San Andreas fault. So these arrows here show that this plate is moving relatively in that direction to that one. In reality, the North American plate is simply moving to the west. The Pacific plate is moving to the north. So here's this natural channel, this natural wash that comes down, hits the fault, the wash is offset. That's because this plate is moved to the north relative to that one. And you can see this wash has been cut and dissected, which is pretty neat. So strike-slip fault or transform faults, what's the difference? Transform is really much larger fault, but it is really a fault that is between a plate boundary. So the San Andreas fault is a transform fault. The Newport-Englewood fault, I would call that a strike-slip fault. They have the same motion, the same movement, but the reason we get that transform nomenclature is because it is a fault that sits right on a plate boundary. So our San Andreas fault is basically taking the Baja Peninsula, ripping away from the mainland of Mexico, and it's moving all this terrain to the north. So what's the difference between fractures and joints? Well, this is the thing, is that geology has some weird terms. Plutons, joints, okay, joint, In the 1960s, we called the joint something else, right? What did they call it back then? I've heard about that. My dad used to tell me. I took a film appreciation course, and we basically looked at Humphrey Bogart movies. So in the 40s and the 50s, a joint was a bar. Watched the Chika Chong movies in the 1960s, and a joint was basically a left-handed cigarette. In geology, a joint basically is what we call a crack, a fracture in a rock. And so fractures basically occur because of weathering. This is the part of the natural breakdown of rocks. It's just one of those natural processes that occurs. And over time, if those cracks were to develop movement, then they would become faults. And that's really the difference between cracks or joints. And so this is kind of neat. This is Devil's Postpile. And these rocks are highly fractured or cracked or jointed, whatever you want to call it. And this is because this rock cooled really quickly. And it cooled so quickly that it cracked. So today, if you were to take like a hot piece of glass out of a kiln, and let's say that glass is almost to the point where it's liquid but solid, and then you immerse it in water, it would crack because it cools too quickly. And that's essentially what happened here in this Devil Postpile here. And we see cracks in rocks where there's no movement, so we just call them cracks or joints or fractures. And that basically ends geological structure. So we'll end here.